drying process, the principles and web handling. After coating, drying is a very important process. Key factors affecting drying of coating on thin films. The following table summarizes some of the key problems associated with the thin film drying process. Each of these will be discussed in more details in the following section. The characteristics that present a challenge during drying. The film characteristics, number one is extensibility or stretching, camber, baggy edges, web width. The coating characteristics like thickness, the viscosity, and the curing requirements. The machine characteristics like the length, width, air handling, and tension on web. The drying is another process as important as coating. The drying of coated web plays a very crucial role in the quality of the end product. There are various methods and principles that are followed to have the most efficient drying. We'll discuss now these one by one. All adhesive coatings, with the exception of hot melt adhesives, are applied to a carrier or to a web in the form of aqueous dispersion or as a solution of solids in an organic solvent. The liquid component of the coating material subsequently have no functional purpose in the end product but serve only as aids to enable the creation of a uniform and smooth coating of the desired thickness. In the coating process, the carrier is unwound and transported through the coating head and the dryer. Usually, dryers are constructed as convection units and have the purpose of evaporating the liquid component. The coating head is called as, that is, the solvent, whether it is aqueous, that is water, or organic. After drying, in the simplest of cases, the finished product is rewound. This is a typical schematic illustration of a coating machine. The significance of dryer as an important part of the production line is immediately recognizable in the schematic. The evaporation of the liquid component is a time-consuming and complex step in the processing of coated material. Now here is a diagram which will explain you how the schematic drawing takes place, how the hot air is circulated. A circulating fan drives the air which has been heated in a heat exchanger via an air guidance system into the product to be dried. The air warms the product on the upper side and where applicable also on the lower side. A certain portion of the liquid evaporates and is carried away by the exhausting air. This exhausting air is partly exhausted to atmosphere and partly mixed with the fresh air and redirected via the heat exchanger into the product dryer. The substrate and the coating center, the substrate and the coating enters the dryer as web at ambient temperature in the dryer. Warm air is directed via air nozzles onto one or both sides of the web. At first, the temperature climbs rapidly and then more slowly as per curve 1 shown in the drawing or the design. The temperature difference between the air and the web causes the web to be warm. As the material temperature reaches, the vapor pressure in the coated liquid rises, causing the evaporation to start. On one hand, the amount of heat which is transferred into the product decreases as the temperature difference between the air and the product falls, while on the other hand, heat is taken out of the coating by the evaporation. These influences continues These influences continue until an equilibrium is achieved and a balanced temperature is reached, known as temperature of constant evaporation. If none of the boundaries conditions such as air temperature, air velocity, air humidity is changed, this temperature will remain constant with further dwell time in the dryer until the liquid has linearly dried out. See the curve here. This point is reached at the changeover from phase 2 to phase 3. In phase 3, the introduced heat serves only to rise the temperature of the substrate further until the temperature of the air is nearly reached in the substrate. Let us take the influences named above like air velocity, air temperature, air humidity and observe the qualitative changes in the drying process. An increase in the air velocity results after the equilibrium of the convective heat transfer. See that in figure 4 now. Here the temperature of the product similarly increases more quickly with increasing air temperature at the start of the process. See a chart here. The phase 2 with the constant temperature is reached at approximately the same time as in previous example. As would be expected, the total evaporative capacity is higher with increased air temperature. Here is another chart showing you the humidity of the air, in other words, the amount of solvent contained in air flowing into the material. Related to our example, this means that for increasing air humidity, the phase 1 is shortened. In other words, the slope of the curve at 100 grams solvent per cubic meter of air is greater than at 25 grams of solvent in cubic meter of air. Here is a chart, have a look again. The reduced evaporation rate leads to a lengthening of the phase 2 as the air humidity increases and thus the time necessary to achieve total drying of coating is increased. Here is a chart. The technical counteractions in the drying of solvents and solids are more complex than the consideration of purely driving out solvent by drying. In the advanced drying process of a nearly pure liquid, the characteristics of the solids in the coating play an ever increasingly important role. To understand the drying, it is necessary to take two phenomena into account. The effect of the surface can be explained by the dilution of the solvent. During the drying process, the portion of solvent is reduced, the surface becomes drier, theoretically achievable partial pressure of the solvent at the particular temperature is no longer reached. For this surface effect, we have already seen the influence of the change in partial pressure reduction of the pure solvent. Here the circulating air humidity is clearly not increasing, but the surface humidity is becoming less, which leads to reduced partial vapor pressure at the coating surface. Here is the graph which explains this. Here is another graph showing you the comparison between drying of a pure liquid and an aqueous dispersion. Dryer technologies. Wave dryers usually are fairly simple process machines despite an apparent merit of design options. So what causes most of the headaches that we in the web process industries suffer? Four problems: the wrong heating system, lousy instrumentation, not enough zones, and pushing the dryer beyond its design limits. The major dryer types are air impingement, parallel flow, infrared radiant, and other radiations. Wave drying process overview. The figure 1 shows four separate regimes. Like you can see, there is a regime of heat up, then there is one constant rate regime, then falling rate, and then at the end it is wave temperature equivalent with the cool air. In the parallel flow dryers and some radiant dryers, the air temperature and humidity change in the machine direction. So the web surface temperature and the drying rate are not quite constant. After most of the moisture is driven off, drying slows and the web surface temperature rises. This is the falling rate regime. The dryer is long enough, the web eventually will equilibrate with the air temperature as in the heat up regime. Most of the heat usually is absorbed by the surface. In the final regime or portion of the process is the conditioning regime in which we equilibrate the web with the room or storage temperature. At best, we can expect an assortment of flatness defects. At worst, the wave gradually can crush the wind-up core. There are three major components to the cost of operating a coating and drying system. Number one, the cost of running the system. This includes fixed costs such as capitalization of equipment, labor, and overhead, and variable costs such as the cost of process heating. Number two, process scrap. The cost of material that go into the coating process but do not result in the product. All coating processes generate process scrap, particularly in the setup stage. Number three is product scrap, material that can run through the process that should have resulted in a product but were found on inspection or further down the value added chain to fail to conform to the critical characteristics. While this can be manifold, common to most PSA coating processes are in incorrect coating wet. The most problems are incorrect coating wet, high retained volatile or incorrect release performance. Since such occurrences involve more than the coating operation, their impact can be far beyond, including loss of customers' confidence and business. Air impingement, multiple nozzle, multiple zone air impingement, including rotation, is the most efficient and flexible forced air design. Here is the design. It is also very cost effective and often can be combined with IR radiant heaters to increase capacity in a limited space or in an existing unit. In air impingement dryer, transversely mounted air nozzles or slots blow plain transverse air jets perpendicular to the web on one or both sides. There are designs that use perforated plates instead of slots or slot nozzle as shown in the figure number 2. Impingement nozzles are simplified with air individual or in groups. In many cases, radiant heaters can be mounted above the web between nozzle. Radiant heaters below the web are not a good idea. The flotation dryer is a particularly interesting variation on the air impingement. Nozzles are mounted facing both sides of the web and boundary layer affects suspend the web in a particular path between the nozzle. Flotation dryers are a bit less efficient than optimally designed impingement units, but the web transport advantages often offset this minor loss. Parallel flow force air is insufficient, inflexible, and a parallel flow air dryer really is acceptable only under two conditions. The discussion below presumes an air impingement dryer operating at constant temperature and air velocity. This is unrealistically simple, but the underlying principles are the same for multiple zone and varied process conditions. Figure 1. Here is the figure. Just have a look. The web temperature profile in an impingement dryer fall into four regimes. They are like initial heat up, constant temperature or evaporative drying, increasing temperature, and plateau or constant temperature. Temperature profiling. Here is a figure. A dryer operating at steady state, a coating with constant solids and volatile composition. A sensor in the constant temperature region will see about the same temperature from the end of the initial warm-up until the beginning of the diffusion limit range. The choice of drying tunnel design depends on adhesive tape, water or solvent base, the desired dry coat weight, the solids content, the operating temperature, the type of web. The other variables are airflow rate, temperature, the exhaust or recycle features. You will find the most popular tunnel designs below. While coating solvent or water-based adhesive, the choice of design must take into account the relative evaporation curve. In case of solvent base, increased amount of solvent must be evaporated at the beginning of the tunnel. In case of water-based coating, the water evaporation is maximum in the middle of the tunnel. Hence, the drying conditions for water and solvent base differ a lot. Water-based systems are more efficiently dried by air volumes rather than air temperature. The temperature gradient throughout the drying tunnel has to be different for water and solvent base. Energy requirement for solvent based coatings are 170 to 200 calories per kg, and for water based it has to be 400 to 500 calories per kg. You will understand that water based needs more calories to dry. Low viscosity water waste can evaporate at 10 to 20 kgs per square meter per hour, and the solvent base can evaporate at 20 to 50 kg per square meter per hour because solvent generally is fast evaporating than water. Another very important criteria is the safety requirement. While drying solvent-based adhesive, the air volume and speed must be large enough to avoid an explosion concentration. The air volume necessary to dry a solvent-based adhesive depends on the lower explosion limit, which is a function of the solvent nature. Hence, it is necessary to heat large volumes of air to keep solvent concentration low. Water-based adhesives do not need such air quantities, thus they are more safer to coat. Many a times there is a very common mistake is to apply too much of it. This leads to the flash off of the upper water layer or solvent layer and thus results in skinning. Water-based drying is generally more efficient with multi-zone ovens programmed for gradual increasing the temperature. Drying channel have slots for air travel situated at 2 to 4 centimeters from the web. Generally, a gap of 12 mm can create a better result as the gap defines the actual drying temperature. The airflow rate should be approximately 60 to 80 meters per second or 180 to 1500 cubic feet per minute. The air temperature at the entrance should be high enough in order to evaporate larger water quantity, and after a decrease of the temperature in the middle, the temperature should increase again at the end in order to eliminate the residual moisture or humidity from the adhesive. Here is a schematic diagram for the dryers. Here it is shown in a much magnified way. Drying tunnel with rollers and air jet over the web. These are design. You can see the idler rolls, the web is passing over the idler roll, and on the top are the the drying tunnel nozzles. In case of a vertical dryer, it looks something like as shown in figure 1 on the right hand side. A typical roller support dryer would generally support the web on either a dead or live shaft idler roll system. The only available force for turning the rollers is the friction between the web and the roller. By arching the roll path, usually the wrap angle will be 2.5 degrees on each roll. The web can be kept in position in positive contact with the roller. A typical roll spacing is between 10 to 24 inches for sensitive webs or to minimize marking or scratching of the bottom side of the substrate. Rolls are often driven at or near line speed. Idler rolls are usually fabricated from either steel or aluminum alloy. The dry temperature and other design factors such as web width, critical roll speed, and deflection considerations determine the material of construction for more sensitive applications with wider webs and higher speeds. Low inertia, low deflection, carbon fiber composite rolls also can be used. Regardless of roll design, the bearings should be external to the dryer box for ease of maintenance and the mounting pads for good roll alignment. Slot nozzles are usually positioned opposite the coating side of the web. They are located 5 to 6 inches apart, about 12 to 25 mm away from the web. The slot width is generally not less than 2 to 3 mm. However, the slot will be wider up to 5 to 6 mm for applications involving solvent-based coating in order to supply larger volumes of air for dilution of solvent air concentration. Arch roll support idlers have a long successful track record. Drying tunnel with rollers and air jet over and under the web. Here you can see the idler rolls, the web, the hot air sprinkling nozzle on the top, as well as the hot air sprinkling nozzle at the bottom of the web also. In case of a vertical coating machine, the in case of a floating dryer, the dryers will be vertical as shown in figure 2 on the right hand side. Air floating dryers. Another view, another picture in figure 3 as well as in figure 4. The concept, the true non-contact air flotation dryers were first introduced way back in 1960s. Factors affect key factors that influence dry design. The challenges are faster line speeds, handling thinner substrates, wider widths, so also the web handling and efficient drying. Some key problems associated with drying of coated film based web: extensibility or stretchability, buggy edges, cambers, edge curl, skinning. No one can accept a flat, uniform film to be pulled out into a wrinkled, neck down string film. While handling polypropylene, polyethylene, or PVC, were to consider some important issues. These films are temperature sensitive. Depending upon the film properties, they start losing stiffness or elongate as the temperature ranging from 65 degrees centigrade to 85 degrees centigrade. Therefore, the drying temperature must be fairly low, which means longer dryers or lower line speeds. However, in some cases, the line speed has to be slowed down for some reasons and the dryer remains hotter. In such situation, the web handling is bit critical. This will generally cause a web break or snap and a undesirable shutdown. Hence, we have to be aware of the film temperature tolerance limits during the coating and drying process. Film loses tensile strength as the temperature rises, hence the tension must be set relatively low to prevent elongation. But then at low tension, the web handling is another concern. Similarly, problem can be caused due to improper air handling design, more particularly in floating dryers. Even in roller supported, poor internal air handling can create web steering or web flutter issues that will result in product defects. Hence, proper air handling, supply as well as exhaust is very crucial. Here the tension control while running stretchable films plays a very important role, and it is recommended that the dryer be dedicated tension zone and is independent of tension requirement in other sections of the machine. Camber. Wave camber is a fairly common manufacturing phenomena for films produced on tender frame systems. Since the wave is not straight, it will tend to take its natural curvature over long unsupported spans. This in turn can present a scenario where the web shifts inside the dryer. For thin films, pulling higher tension to mechanically straighten the film may not be possible. Frequently, the only tenable solution is to make the idler or the nozzle wider to allow for the shift while maintaining roll contact and or uniform air cushion contact within the dryer. Buggy edges. This condition can result in the coating picking off on the nozzle, which is in turn can create coating defects and dryer cleaning issues. To some extent, this can be addressed with adjustments in nozzle spacing. However, due to the method of web support, there are limits to the amount of clearance that can be allowed before losing control of the web pattern. For roll support dryers, baggy edges are less of a common unless the dryer is equipped with bottom side impingement nozzles, in which case turbulence from edge flutter could potentially lead to defects. Web width. Wide, thin film webs present a number of drying challenges. All the conditions discussed above will be amplified or increased in a wider way. This is predominantly due to the fact that wide webs are more sensitive to air flow. Here is a diagram you can go through how the tapered air distribution header can help. The tapering will help in maintaining the air pressure across the width, across the length of the machine. Here is another view. Likewise, the method of exhausting air from the dryer enclosure becomes even more critical when handling wider waves. Here is a diagram explaining you the same. The other considerations while ensuring proper drying, the coating characteristics, the coating thickness. Thick coatings on thin film can present problems. As a coating dries, stresses are generated in both the coating and the substrate. The coating itself may deform the substrate as it is dried, that is, edge curling on the adhesive coated film. Edge curl can also occur when coated widths are less than the full web width, since the drying stresses will vary between the coated and uncoated portion of the web. Again, some of these problems can be addressed via tension control, but only if the dryer is a controlled tension zone. The other considerations while ensuring proper drying. Here is a design that will explain you quiet zone for controlling evaporation of solvent in thick solvent. Also, bottom side heating is often used in quiet zones to prevent both gradual heat transfer and coefficient dilution air without directly impinging on the face side of the web. Here is a diagram how this could be done. Single side flotation nozzle combined with dilution air bars. Thin coating and coating viscosity. There is no doubt that tends towards thinner coating have presented challenges to coating equipment manufacturers as they are forced to develop and provide application techniques suited to the coatability of the formulation. But dryability of thin coatings must also be assessed when formulating new coatings. Lower coating weights leave fewer margins for error. Coating ununiformity is important, and then coating may be more sensitive to contamination, whereas thicker coatings may be able to hide a defect more readily. Special cleaning of the dryer and ductwork. Here is a drawing for customs accumulator style dryer used to prevent face roll contact of the coated side of the web. This side, this is the accumulator. Machine characteristics, dryer length, longer dryers, whether with flotation or roll support. Increasing the width of the air flotation nozzle is one method of allowing for such tracking errors. Drying tunnel with roller and conveyor belt. You can see there is a conveyor belt just below the web, immediately above the idler. This helps the web handling to a great extent. Here is another design, drying tunnel with air flotation only. You will see series of nozzles on the top, series of nozzles at the bottom with no supporting idler roll inside the drying tunnel. Some drying tunnel design faults unnoticed. Gap between the nozzle and web. Case 1. The gap is around 12 mm. You will find that this is acceptable. Now see, consider case 2 where the gap is more than 25 mm. This is not acceptable because the drying efficiency will decrease to a very great extent. Case number 3 where the gap is hardly 8 millimeters or low. This is also not acceptable because the efficiency or the drying will not be correct, and there are chances that due to excess of exhaust or due to air pressure loss from the blowers, the coated web can get in contact with the nozzle and chances that it can get stuck. So this is not acceptable. Some dry design faults unnoticed. The tunnel is too large or too small. Now you see case 1, this one is the acceptable kind of design. Now you see case number 2, this is not acceptable. The tunnel is too big. The gap or the volume of a tunnel below the idler is too large, and this is going to consume extra energy because in order to maintain the temperature inside, a large amount of air will be required to be heated. Now case number 3, even this is also not acceptable. Here you will see that the tunnel size or the depth is too low. The idlers are practically touching the tunnel at the bottom, and this is also not acceptable. Now here you see an animation of some dryer faults like the air velocity. The correct velocity is what's shown in case 1, approximately 1500 cfm. What happens if the velocity is more than 2000? The coating will be disturbed by the amount of air, and that is how we can expect some problems. Thank you very much for attending this video lecture. Namaskar.